Welcome to the physics class for March the 8th. As usual, let's talk about a couple announcements first. All right, the plan for the next couple weeks is we are going to do chapter 18. We're going to start into chapter 18 today. Next time we meet, which will be second time this week, we'll finish up chapter 18, and then we'll be ready for the test. So notice we are skipping chapter 17 completely. And hopefully you guys remember that we've also skipped pretty large sections of chapters 19 and chapter 16. We're not doing everything in there. There's just not enough time in the year to do all the cool stuff that we really would like to do. So this week, chapter 18, first time we meet next week, we'll spend one day just doing review. And then after that will be the test. So be prepared. The second time that we meet next week, either Wednesday or Thursday, depending on whether it's A day or B day, will be a test that will cover chapters 19, 16, and 18. And then the week after that is the end of the term. Okay, so with that in mind, please remember that you got to get all your late homeworks and quiz retakes done before we take the test. And if you want to go for any extra credit, you got to do that before the term ends, which is coming up real soon. Speaking of extra credit, you may remember that there was an extra credit opportunity that I had posted in Canvas where the two girls, they had made the video where the one girl is looking at the Kindle wearing the polarized sunglasses and she can't see anything. And the other girl is looking at the Kindle wearing the non-polarized glasses and she can see things. So I had told you guys that if you wanted to get extra credit, you needed to do that by today. I've decided that I'm going to just push that off because there's so many things we need to do today. We just don't have time to talk about it. So if you want to get that in for extra credit, I will extend it towards the end of the term. But you can't just say, well, the reason is because the Kindle is polarized. You got to tell me, how does LCD, how does a liquid crystal display work? You got to draw me a cross section of an LCD screen and show me what's taking place in there and explain to me why it has to be polarized, why it wouldn't work if it wasn't polarized. Okay, so I will extend that out. All right, I think that's it for announcements. Let's go ahead and talk about last night's homework. So here are the answers to the problems that you haven't already looked up. The first question, the one that I wrote and that I put in Canvas, let's talk about that one together. And that was the question about how was it that Ole Romer was able to figure out what the speed of light was way back in the 1600s. How did he do that? So rather than me talking about it, let's see if you guys can come up with it. Who have I not picked on for a while? Let's see. Austin, I don't think I've picked on you for a while. Can you please unmute yourself and tell us, how did Ole Romer do it?
Well, he was measuring the period of one of Jupiter's moons, and there was a difference, like different people had different numbers for it. And it was because the light was taking a long time to travel from there to Earth. And so he was able to calculate how far the light had traveled in that time to like make that time difference.
Okay, all right, good. Now, in your homework tonight, I'm sorry, not your homework, in the quiz that you need to take for chapter 16, quiz 16B, one of the questions that I ask is for you to do the actual calculations. Now, in the book, they talk about one way of doing it. I think their way is overly complicated. I think there's a much simpler way to do it. So when you take the quiz today, and I ask you to calculate the speed of light as if you were Ole Romer, please don't do it the way that it's in the book, because if you do, you're going to get a different answer than what I put in for Canvas. The way that I want you to do it is I want you to assume that Ole Romer measures the period of IO when the Earth is in this position right here. Okay, so the IO goes behind Jupiter, and when it does, the light has to travel this far. And then you wait 1.8 days, and IO goes all the way around. Okay, and now it's going to pass behind Jupiter a second time, but 1.8 days have passed. And during those 1.8 days, the Earth has moved. So the Earth is now over here, but the distance is still the same because the Earth has moved perpendicular to the distance that the light travels. So the number that you get for the period of IO when the Earth is in this position will be the correct period for IO. And so we're going to assume that that's 1.8 days exactly, even though it's actually 1.8 something, something, something. We're just going to assume that it's 1.8 days exactly. All right. And then 3 months later, we're going to assume that the Earth is now in this position right here. And so the first time that IO travels behind Jupiter, the light has to travel this far. And then 1.8 days later, when it goes around and comes behind Jupiter the second time, Earth is no longer where it was. Earth is now over here. Okay, so that second light ray has to travel farther than the first light ray traveled. And when we measure the time, when we measure the period of Jupiter, we get a number that's 13 seconds longer than it was when we measured it right here. And the reason is because that second light ray had to travel this distance here that the first light ray did not have to travel. Okay, so if you just take that from that information and knowing what the distance from the sun to the Earth is, which by the way is written down here, it's in the back of your book, but I've written it for you down here. So knowing that you can calculate how far did the Earth travel in 1.8 days. So in 1.8 days, the Earth went from here to here. So that extra distance, that is how far that second light ray had to travel that the first light ray did not. And so if it took the second light ray 13 seconds longer than it took the first light ray, then that means that whatever this distance is, if we divide that by 13, that will be the speed of light. So all you have to do is figure out what that distance is. But that should be quite easy. I mean, because you know that it takes the Earth 365 days to go all the way around the circle. And you know that the circumference of the circle is 2 pi times the radius. And you know that the semi-major axis of the Earth is 1.496 times 10 to the 11th. So we know what the radius is. So we can figure out how far does the Earth travel in 365 days. So from that, we can figure out, well, how far does the Earth travel in 1 day? And from that, we can figure out, well, how far does the Earth travel in 1.8 days? So it's pretty straightforward to figure out how far the Earth travels in 1.8 days. Just take that and divide it by 13 seconds, and that will tell you what the speed of light is according to the measurements made by Ole Romer, which will be different from the currently accepted value of speed of light, but not much. I mean, it's actually surprisingly good. So when you take the quiz 16B, do not use the method that they describe in the book. I mean, their method is a good method, and you can make some strong arguments for why their method is probably more statistically believable than the method that I just described. Their method might actually be a statistically better way to do it, but I think it's overly complicated. I think if you just do it this way, you can get a number that is a valid number, and I think it's pretty easy to get. So when you do it in the homework, if you do it the way the book describes it, then your answer will be different from the answer that I put into Canvas because I did it this way. And so this is the way that I want you guys to do it too. All right, so hopefully that's going to be straightforward. Okay, so let's go back to the homework problems here. All right. Now, problem number 16, I need to warn you. There was a typo in the book. that I had forgotten about. I forgot to warn you guys. So in the book on problem number 16, they claim that the speed of, so they say that there's some galaxy, and so we're measuring the light coming from this galaxy. And they say that this galaxy is moving away from us. Why does my screen not want, every time I change my screen, I have to turn off annotation, then I have to turn it back on again, and it doesn't want to come back on. So they say that the speed of the galaxy is 6.55 times 10 to the 16th meters per second. Now, I would hope that you guys looked at that and you said, what? Because hopefully you guys know from your previous classes that nothing can travel faster than the speed of light. That's something that we are going to talk about in this class, but not for a couple of weeks. But it is true that nothing can travel faster than the speed of light. So when they say that the galaxy is 6.55 times 10 to the 16th meter per second, you should look at that and say, whoa, there's something wrong there. Well, it's a typo. Okay, what they really meant was times 10 to the 6th. Okay, so times 10 to the 6th is what they should have written. So can you guys do me a favor right now? Open up your books. Now, hopefully, the previous year students have already done this for you. So hopefully you saw what they did. But I want you to go in, open up your books to page 447, page 447, and go to 16. And I want you to cross out the 10 to the 16. And I want you to write in 10 to the 6. And then I want you to write the word typo. So that way next year students will hopefully not be confused by it. All right, so if you use 10 to the 6th as the correct multiplier there, then you should get 497 nanometers as being the correct answer here. Now, with that being said, let me ask, if you could only see one problem worked through, what would you want that one problem to be? Please type it into the chat box. And if that problem is number 16, I'll be glad to do it for you. I need a bunch of answers here. So I am seeing a vote for 16. I'm seeing a vote for 52. I'm seeing a couple of votes for 16 now. Some of them are private messages, so I'm seeing them, but you're not. Let's get a couple more votes here. Right now, it's kind of even between 16 and 52. Okay, looks like 16 is winning now. All right, 16 is the clear winner. So we'll do number 16. And then Will, you wanted to see 52. So if you want to see it, then how about stay on after the class ends and we'll talk about it then. But let's do number 16. All right, and let me open up a whiteboard. All right, so what we've got here is us, and here is this distant galaxy. And they claim that the galaxy is moving away from us with a relative speed of 6.55. Boy, that's terrible. My screen is just, when I push the erase button, it doesn't recognize it. Okay, 6.55 times 10. So they claim it's 16, but now we realize it's actually 6 meters per second. All right, and they say that the wavelength that is emitted is 486 nanometers. Now, that's not actually what they say in the book. They say 4.86 times 10 to the negative 7 meters. That's what they say in the book. But that's the same thing as 486 nanometers. Okay, so the question then is, what wavelength will we see when the light gets to us? Okay, so we need to know what the equation is. So we can look in the book or look in our lecture notes. And now we could use the original wavelength equation or the original Doppler equation. We could say that FD equals Fs times V minus Vd over V minus Vs. And remember, with light, it's impossible to tell who's moving, the detector or the source, because the medium for light is not air. So, I mean, with sound, you can feel the wind on your face. So you know whether you're moving or whether the other person's moving. But light, the medium is not air. The medium is the fabric of the universe. You can't feel that on your face. So you have no way of knowing who's moving. So what we did was we defined that the source velocity, we're just always going to say that that's 0. And any velocity that is taking place, we're assuming that it's because it's the detector moving. Okay. And V here is really the speed of light. Now they give us the wavelength, the equation wants for frequency, but we know how to convert wavelength into frequency because we know the wavelength is the speed of light divided by the frequency, right? So what we could do is we could convert this into wavelength or convert this from wavelength into frequency. Okay, so frequency would be C over lambda. And we convert it in here, we do the math, we get an answer out in terms of frequency, and then we just convert it back into wavelength. We could do that. But why? Because we went to all the trouble last time of coming up with a new equation. I mean, it's not really a new equation, it's the same equation, but we just converted all the F's into lambdas, and we converted the VD into a VR. Okay, so let's use this new equation. And that one says that delta lambda is equal to plus or minus V over C, and that's V relative, times lambda. So this is the Doppler equation simplified down for the case of light. All right, well, we know what the original lambda is. We know what V relative is. We know what the speed of light is. Okay, now this plus or minus here, that sometimes bothers people. So what I like to do is I like to say, well, let's just work with absolute values. And then we'll look at the picture and we'll think about whether we want to add or whether we want to subtract. Okay, so let's just say that if we work with just absolute values, so the absolute value of the change in wavelength is going to be V relative times lambda over C. All right, so we get out our calculator, and V relative is 6.55 times 10 to the 6th, not the 16th, okay, times lambda, which is 4.86 times 10 to the negative 7. Okay, we're going to divide that by the speed of light, which is 3 times 10 to the 8th. Okay, so what I get is that delta lambda is 1.06 times 10 to the negative 8 meters. That is how much the wavelength is going to be shifted. Now, so I'm either going to add that or subtract that to the original wavelength. Okay, so either add or I might subtract. Okay, how do I know which one it is? Well, if they tell us that the galaxy is moving away from us, then you guys know from our previous work with sound, when we did the Doppler equation with sound, we know that if something's moving away from us, we hear a lower frequency. Now, remember that frequency is inversely related to the wavelength. So that means if the frequency gets lower, that means the wavelength is longer. So that means that the light that we see is going to have a longer wavelength. So that means we have to add this. So we're going to add delta lambda to whatever the original lambda was. So you see how this works? So if you just work in absolute values here, and then look at the picture and then just logically ask yourself, okay, is it moving towards us, away from us? Therefore, do we expect a longer or shorter wavelength? Okay, so I'm going to take this number that we just got, and I'm going to add that to the original wavelength. So the original wavelength was 4.86 times 10 to the negative 7. And when I do that, the answer that I get is 4.97 times 10 to negative 7 meters, which is the same thing as 497 nanometers. All right, so let's look let's look and make sure that that matches what we had here. Hey, what do you know? It matches. Isn't that reassuring? Okay, so 497 nanometers, which is the same thing as 4.97 times 10 to the negative 11 meters. Okay, there we go. So we did in fact get the right answer. All right, so you guys good on this? Tell you what, can you give me thumbs real quick? Everybody use the reactions tab down at the bottom of your thing. Okay, good. I see a lot of thumbs. Okay, reassuring. Okay, well, let's go ahead and move on. So if you do have number 20, I think we should take a minute and talk about number 20. That's important. And I'll 18 and 20. Okay. With these problems, you need to understand this diagram right here. Okay, this diagram. Okay. If you understand this diagram, then that's all that I really expect you to know. So red, green, and blue are the primary colors that you use when you're doing an additive process. So there's two ways that you can mix colors together. You can mix them together versus an additive process. Okay, and what that means is you're shining lights. A shining light. Okay, so we're going to take red light and we're going to shine it on the wall. We're going to take green light and shine it on the wall. We're going to take blue light and shine it on the wall. When we do that, they're going to overlap each other and you're going to get white. That's an additive process. Okay, you're adding the colors. Now, the other option is you could use a subtractive process, which is the way that paints work. Paint pigments, they subtract. Okay, so if you look at red paint, the way it works, the reason it's red is because it's subtracting out all of the other colors. Anything that's not red, it's absorbing it, and the only thing that it's reflecting is red. Okay, so if you take red paint and you mix it together with green paint and you mix it together with blue paint, those pigments are going to be subtracting out all of the colors. So if you mix red, green, and blue paint, you will get black. But if you mix red, green, or blue lights, if you shine lights on the wall that are red, green, or blue, then you'll get white. So make sure that you understand whether you're using an additive process or a subtractive process, because the results are very, very different. Now, the book does, I think, a pretty good job of describing this, and so I didn't even talk about it last time. I just trusted that you guys would read it. Now, when you take the quiz tonight, the quiz 16B, I did put a couple of problems in there just to make sure you understand the difference between an additive process and a subtractive process. So hopefully you guys will be good on that. Okay, so if you have any problems or if you have any questions about any of the other problems from the homework, wait until the end of the class here. And after everybody else is logged off, I'll be glad to talk with anybody who wants to talk to go over last time's problems. All right, so let's talk about the new stuff. Today, we are going to go into chapter 18. So notice we're completely skipping chapter 17 totally, which breaks my heart because there's some really good stuff in there, but there's not enough time in the year to cover all the good stuff in the book. So we're going to go to chapter 18. Chapter 18 talks about refraction and lenses. Today, we're going to talk about refraction. And then next time we meet later this week, so Wednesday or Thursday, depending on whether it's A day or B day, that's when we'll talk about lenses and how they work, how glasses and microscopes and telescopes and all that work. But today, we're just going to focus on refraction. Now, the word refraction should not be a new word to you. We have talked about it before. This is the diagram that we used when we talked about it before. And now all waves diffract, or I'm sorry, refract. All waves refract. It's not just light waves, but usually when we talk about light refraction, normally light is the example that we use. So we're going to assume that we've got some air and we've got a light ray that's traveling through the air and it hits an interface with something else. It might be water, it might be glass, doesn't matter. It's just something that's not air. Okay, so not air. Okay, and now remember refractive index? We've talked about refractive index. That's the lowercase n. Refractive index is defined as the speed of light in a vacuum, which is c, divided by the speed of light in whatever medium you have. Okay, and so the speed of light is always going to be fast. The speed of light in the medium is always going to be less than the speed of light in vacuum. So this n value is always going to be greater than 1. Now, air has a refractive index that is almost exactly 1. It's actually like 1.00 something. But if all you need are 3 sig figs, then you can just call it 1. And then the one that's not air, tell you what, let's say that it's water. And in the book, they give you a table where you can look it up. And you'll find that the refractive index of water is about 1.33. Okay. All right. So what we're going to do is we're going to look at this light that's coming in at an angle. And we see that when it hits this surface, then the light that gets transmitted, it goes in a slightly different direction. And so what you're seeing here, this is refraction. Now, what is not shown in the diagram is that whenever a wave encounters a boundary between two medium, some of it is transmitted, but some of it is also reflected. Right? So we are only looking at the transmitted light, but do not forget that there's also going to be some light that's reflected. Now, the reflected light, that is covered in chapter 17, which we've skipped. So let me just tell you the way you need to know is that whenever you have reflection, if you were to draw a line where this line is perpendicular to the surface, this angle here, we're going to call this theta incoming, and this angle here, we're going to call this theta reflected. The reflected angle is always going to be equal to the incident angle. Basically, that's all you need to know about chapter 17. There is some other cool stuff we could talk about, but that's all the part that's really important. So the incident angle is equal to the reflected angle. But let's say that we're not interested in the reflected light. We want to focus all our attention on the transmitted light. Okay, so Gia, that's okay. Don't worry about it. All right, so what we're going to do then is we're still going to use this same line here as our reference line. This is the line that is perpendicular to the surface. This angle here, we're going to call this theta 1. And this angle here, we're going to call this theta 2. And they are not equal to each other, but they are related by an equation, which is known as Snell's law. And it's a very simple equation. Now, the book doesn't derive the equation. Shame on them. You guys, if you've learned nothing else, you should hopefully have learned that I think that we need to derive every equation that we use. That's what makes physics physics, is deriving the equations. So when we take the test next week, it's entirely possible that the equation that I'm about to derive might be something that you need to know how to derive for the test. So I'm hoping that you will open up a new page on your notebook. And up at the top of the page, I want you to write derivation of Snell's law. Right? So what I'm going to do is I'm going to take this picture and I'm going to zoom in on it just to make it a little bit easier to work with. And Now, Snell's law is very easy to derive if you understand Huygens principle, which hopefully you guys do now, because you've done chapter 16 where we talked about Huygens principle. So hopefully you understand it. Tell you what, let me go back here. Let me back up to here so we're going to do Huygens principle, and we're going to do it for a light ray that has not yet hit the surface. So we're going to say that we've got, so here's a whole bunch of dots. So Huygens said that this light ray that's out here that hasn't hit yet, you can treat it as if it's a whole bunch of dots. So let's look at this dot. So he is a new source of a new wavefront. And so if I were to draw that new wavefront, it's going to look like that. But he's got lots of neighbors. And each of his neighbors is also the source of a new wavefront. Okay. And he's got neighbors on the other side too. So when you add up all of these neighbors, they all combine together so that the original wavefront was here, but then one wavelength later, what we've got is a straight line. And then we repeat the process. And so again, all of these guys put out light like this. Okay, and so then the new wavefront looks like this. So that's why the wave propagates. Now, the interesting thing is what happens when you get right here. So this is now a new source of a wavefront, but it's in a new medium now. So when we draw this half circle, the distance from the dot to the circle is now going to be smaller than it was before, because the wave is in a new medium now where the speed of the wave is slower. So this distance here is going to be less than this distance out here. So all of these guys out here, they're still doing what they did before. They're traveling along like this, but any dot that's in the medium, it is going on along like this. So it's traveling more slowly. And because the wave front here has this kink in it, it's going to be traveling in a different direction. Okay, so with that being said now, so let's go back to my zoomed in picture here. And let's derive Snell's law using Huygens principle. So what we're going to do is we're going to say, okay, this guy right here is the source of a new wave, and it's going to look like this. And so this distance here is wavelength in the new medium. So this is medium number 1 up here. My screen is being finicky here. All right, and down here is medium number 2. So the wavelength here is the wavelength in the new medium. And up here, where we had, this is where we had the Huygens principle is taking place. So this is the wavelength in the original medium, okay? And because this guy has lots of neighbors here, each one of them is doing the same thing. So they're going like that. And this guy up here has lots of neighbors, so they're all doing the same thing. Okay. All right. Now, the wavelength is equal to the velocity divided by the frequency, which is equal to the velocity times the period, because you remember the frequency is 1 over the period, right? So that means the period is 1 over the frequency. So the wavelength in any medium is the velocity of that medium, is the velocity of the wave in that medium times the period. Now, the period of a wave does not change. When a wave travels from one medium into another medium, the frequency doesn't change. The speed of the wave changes, therefore the wavelength changes, but the frequency of the wave does not change. If you have some surface and you've got 3 waves per second hitting it from this side, you're going to have 3 waves per second going out the other side. Now, the wavelength going out the other side may be different, but the frequency is going to be the same. That means that the period is going to be the same. So if we were to draw a triangle that looked like, hang on a sec, every time I switch here, I have to go through this weird process to get it going again. Okay, so this distance right here is lambda 2, which is the velocity. Hang on, so this is the velocity in medium 2 times the period, which is the same period as it was before. Okay, this distance right here, let me do this in a different color. This distance right here, this is the wavelength number 1, which is the velocity of the wave in medium 1 times the period, which is the same period. The period here and the period there, they're the same because we just got through saying the frequency doesn't change, therefore the period doesn't change. All right, so what I'm going to do is I'm going to draw me 2 triangles. I'm going to draw a triangle that is a blue triangle. And this here is 90 degrees. And this angle here, I'm going to call this my blue theta. Now, I'm going to do the same thing down below. I'm going to draw a red triangle right here. And I'm going to say that this angle here is my red theta. Okay. And this is a right angle right here because the direction, the direction of propagation of the wave is always perpendicular to the wave front. So this angle here is 90 degrees. This angle here is 90 degrees. So what I've got is I've got a red triangle and a blue triangle, but notice they both have the same hypotenuse. They share a common side. They have the same hypotenuse. All right, so now let's look at the red triangle. So we know that the sine of the red angle is equal to the opposite side divided by the hypotenuse. And the opposite side is the wavelength, which is V2 times T. Okay, and then we have to divide that by the hypotenuse. So the sine of the red theta is V2 times T divided by the hypotenuse of the red triangle. Now, what about the blue triangle? Okay, well, we know that the sine of the blue theta is equal to the opposite side, which is the wavelength, which is V1T, divided by the hypotenuse. And remember that both triangles share the same hypotenuse. So that means that the blue H and the red H are the same H. All right, so what we can do then is we can rearrange this. So we can say that H equals V1T divided by the sine of the blue theta. And I can rearrange the bottom one to say that H equals V2 times T divided by the sine of the red theta. Now remember, the red theta and the blue theta are not the same, but H is. H is the same. So what that tells me is that V2T times the, or divided by the sine of theta must be equal to V1T divided by the sine of the blue theta. Now, rather than calling them blue theta and red theta, tell you what, let's call the blue theta, we're going to call that theta 1, and the red theta, we're going to call that theta 2. All right, so there we go. We have an equation which is not yet Snell's law, but we're 90% of the way there. So I'm going to pause for just a minute, so give you time to catch up. So everybody understand what I did? I said that the sine of the angle is equal to wavelength over H, and the wavelength is V times T. So I did that for the red angle down here. I did it for the blue angle up here. I solved for H and I recognized that it's the same H in both cases. So bingo, that's what we got. So V2T over sine theta 2 is V1T over sine theta 1. So at this point, I'm thinking I want to open up a new whiteboard and make it a little easier here. So I'm just going to rewrite what we just got. So V2 times T divided by the sine of theta 2 equals V1 times T divided by the sine theta 1. All I did was rewrote what we got before. Okay, so we're almost there. So notice we got a T on each side. So if we divide by T, they go away. Next thing I'm going to do is I'm going to use the definition of refractive index. Refractive index, hopefully you recall, is defined as the speed of light divided by the wavelength in whatever medium you're at. So that means that N1 is equal to C over V1, and N2 is equal to C over V2. So I'm going to rearrange that. So this one I'm going to rearrange to give V1 equals C over N1. And this one I'm going to rearrange to get V2 equals C over N2. Okay, I'll give a pause for a second to let you catch up on that. Wherever I see a V2 here, I'm going to replace it with the thing that I know V2 is equal to. Wherever I see a V1, I'm going to replace it with the thing that I know V1 is equal to. So that's going to give me C divided by N1 sine theta 1 equals C divided by N2 sine theta 2. We're almost there now. So we got a C on each side, so that goes away. So that leaves us with 1 over N1 sine theta 1 equals 1 over N2 sine theta 2. So if we just flip both sides, then voila, we have Snell's law. We have N1 sine theta 1 equals N2 sine theta 2. This is the relationship that's known as Snell's law. And we're going to be using this equation a whole lot, especially in tonight's homework, but even later, we're still going to be using it later too. This is Snell's law. So let's go back to my PowerPoint. Right, so in the book, they just give you Snell's law. They don't tell you where it comes from. Shame on them. They should have. All right, so let's see how we use it. Let's do something like you would see in your homework tonight. We've got a light ray that's coming along and it hits a pane of glass. So imagine this is just a really thick window. And so we're going to have two separate refractions here. One refraction is going to occur at this interface right here. And then the other one is going to occur at this one down here. So for right now, let's ignore that one. Just focus all our attention on this one right here. So we know that air has a refractive index that's so close to 1 that if all you need are 3 sig figs, you can just call it 1. So that's going to be N1. Now it's going into the glass, so that's going to be N2. So for glass, we have to look up what is the refractive index of glass. Now, when you look in the book, because I know you always look in the book before you do the homework, you're going to see that they give you a table in there. And in fact, let's go down to here. Okay, so you'll see that they give you a table and there's a lot of different types of glass. There's crown glass, there's quartz, there's flint glass, and this is just 3. There's even more than this. So there's a whole bunch of different types of glass. So in the problem, they'll have to tell you what kind of glass it is. Let's keep it really simple here. Let's just say that whatever the refractive index of the glass is, let's just say it's 1.5. Okay, so we're going to assume that it's coming into glass as a refractive index of 1.5. And so in your homework tonight, they'll tell you what the incident angle is. So let's pick a number. Let's say that it's 53 degrees. And by the way, this theta here has to be measured from the perpendicular. Okay. You don't want to measure it from the surface, you measure it from the perpendicular. Now some of you might say, wait a minute, Mr. Hendricks, when you did the derivation, didn't you measure it from the surface? So maybe we should talk about that really quick. So, well, actually tell you what, let's finish this problem. And then I'll go back and I'll explain to you why the theta that I used and the theta that the book is using really are the same theta. But first, I want to finish this problem that we just started. Okay. Well, I'm thinking that we are in a position where we can do it. We know Snell's law, and we know what N1 is. We know what theta 1 is. We know what N2 is. The only thing we don't know is theta 2. So from this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? All right, well, let's see. Let's do the algebra using the letters, not the numbers, because hopefully by now you guys are in agreement that that is in general the best way to do things. All right, so what I'm going to do is I'm going to divide both sides by n2. And now I've got sine theta, but I don't want sine theta, so I'm going to take the inverse sine of both sides. Okay, so that goes away, so it leaves me with theta. So what I get then is theta equals the inverse sine of n1 sine theta 1 divided by n2. So now all I have to do is just plug and chug, right? So I get out my calculator and I say, and now make sure your calculator's in degrees, not radians, because the angle was given to us in degrees. So we better make sure our calculator matches that. So I want to do the inverse sine of n1, which is 1, times the sine of theta 1, which is sine of 53, divided by n2, which is 1.5. Okay, so I get that theta 2 is 32 degrees. Okay. So if the incident angle is 53 degrees, and if it's glass with a refractive index of 1.5, then the transmitted ray will be transmitted at an angle of 32 degrees. And remember, this is all relative to this perpendicular line here, which is called the normal. Remember that when a mathematician says normal, they don't mean not strange, they mean perpendicular. All right, so we see that the light gets refracted when it enters the glass. Well, guess what? The light also gets refracted when it leaves the glass. So this time, N1 is going to be glass. So that's 1.5. N2 is the air this time. So that's 1.0. This theta and this theta are going to be the same because they're alternate interior angles. So theta 1 now is 32 degrees. So what we can do is we can use Snell's law to find out what is theta 2. And I'm sure that you guys will not be surprised to find that when you do that, you get back the exact same 53 degrees that we got before. Okay, so what happens is that the incoming light ray and the outgoing light ray will be parallel to each other, but only when they leave the glass. When it's in the glass, then it's not parallel. But when it leaves the glass, it's going to be parallel, but it will be offset a little bit. If I take this guy and I follow this line here, you'll see that they're parallel, but they're offset. And the thickness of the glass determines how much the offset is going to be. If it's a really thick glass, they're going to be offset by a lot. If it's a really thin glass, not so much. Okay. So as long as we're talking about a pane of glass where the left edge of the glass and the right edge of the glass are both straight lines, they're parallel to each other, then the outgoing ray will be parallel to the incoming ray. But what if it's not a window pane like that? What if instead of being a window pane, what if we have a piece of glass that looks like this? Okay, then you're going to have the incoming light ray here, and then you're going to draw the parallel so you can figure out what the refracted ray looks like. And then here, I said parallel, I meant perpendicular. So here we draw the perpendicular again, and what you're going to find is that in this case, if it's a glass that's shaped like this, the outgoing ray is not parallel to the incoming ray. And so this is a lens, and this is not a lens. Okay, and lenses can be used to focus light. And so like this, I mean, you guys have all done this, right? You take a magnifying glass out in the backyard on a sunny day, and you can light paper on fire, or you can burn ants, which is what most students tend to do, which is really, that says a lot about the mentality of people. So let's just focus it on paper. All right, so we can start fires if we have a big enough magnifying glass. Right now, this is what we're going to talk about next time. We're not going to deal with lenses. So Aurora is saying that she cooked a starburst that way. Oh, that's cool. That's unique. I'm glad to see that. Okay, so in our homework tonight, we're not going to worry about lenses. We're going to stick with things like this. And hopefully you realize that if you know how to use Snell's law, it's going to be quite easy. Now, things get really interesting when you've got a light ray that starts off inside a piece of glass or water that has a high refractive index, okay? And then you're going from high into low. Things get really, really interesting in that case. Let's take a look at how that can be, okay? So let's assume that we've got water and air, and let's assume that we got a scuba diver with a laser pointer. And so the scuba diver is pointing the laser pointer up out of the water. So here's the laser pointer. All right, so if we do the math, let's suppose that theta 1 is some number that's relatively small, like say 15 degrees. All right, and N1 is 1.3, N2 is 1.0. So if we apply Snell's law in this case, we'll find out what theta 2 is. In fact, let's do it. This gives us a little more practice here. So we're going to solve for theta 2. So we're going to get the same thing we got before. We're going to get theta 2 is the inverse sine of N1 sine theta 1 divided by N2. So N1 is 1.3, theta 1 is 15, N2 is 1.0. So when I put this in my calculator, I do the inverse sine of 1.3 times the sine of 15 divided by N1, which is just 1, so I don't need to worry about it. So what I get is that theta 2 is 19.7, which I'll round off to be 20, but let's not worry about that. Notice the refracted angle is bigger than the incoming angle. So if you look over on the right side, I think you can see where this gets interesting. If we keep increasing the angle, there is a point where the angle is going to be such that the outgoing angle is going to be 90 degrees. What happens if you go past that point? So, and by the way, if you get to the point where the incoming angle gives you an outgoing angle of 90 degrees, we have a word for that. We call that the critical angle. So at the critical angle, theta 1 is just the right size so that theta 2 is 90 degrees. What happens if you go bigger than that? Well, if you try doing it on your calculator, you're going to get an error message, because what's going to happen is you're trying to take the inverse sine of a number that is bigger than 1. And when you do that, your calculator is going to say, error, you stupid human, you can't take the inverse sine of a number that's bigger than 1. Well, what that means in physics is it means that there will not be any transmitted light at all. What you will have is you'll have 100% reflected. Okay, and when I say 100%, I mean absolutely, positively 100%. Now you might say, well, doesn't a mirror give you 100%? Actually, no. Okay, so if we draw a mirror, and so here's a light ray, comes, it hits the mirror. So most people assume that 100% of the light is reflected, because obviously with the mirror, you don't get any transmitted because the mirror has that silver surface. So you don't get any transmitted. So it is true that with the mirror, you have 0% transmitted. But it is not true that with the mirror, you have 100% reflected. What happens is that some light gets absorbed. Okay, maybe not a lot, but enough that if you were to have multiple reflections, that you would have a problem. So let's assume here that we got a whole bunch of mirrors. Well, let's just say we have 2 mirrors. And so here's air in the middle. And here's a mirror on this side, and there's a mirror on that side. So we're going to send in a light ray, and it's going to bounce off the mirror and bounce off this mirror and bounce off that mirror and bounce off this mirror and bounce off that mirror. Each time it bounces, you lose a certain amount, even if you only lose 1%. Okay, let's assume that every time it bounces, you lose 1% of the light, it gets absorbed. Well, if you do 100 bounces, then you're not left with very much light. Now, it's not going to be 0 in that case because it's 1% of the amount that you've got. So you got 99% here, and you get 98.1% here, and you get 97.2% here. So, but after a couple hundred bounces, you don't have any light left. Okay. If you want to be able to bounce this thing off a whole bunch of times, here's a really neat trick that you can do. Instead of using mirrors, take glass, okay, and so this is glass with a high refractive index, and surround that by other glass that has a low refractive index. Okay, so, all right, so what we've got here is we got glass in the middle, surrounded by glass on all sides. And maybe some of you might recognize that what I'm describing is a fiber optic cable. All right, so now look what happens when we have a light ray that comes in. If that light ray hits it at an angle like this, so the angle is bigger than the critical angle. So what will happen is we will get 100% reflection. And I do mean 100%. So there will be no absorption at all when that reflection occurs. And so we get 100% reflection, then it bounces here and 100%, here 100%, here 100%. So this thing can bounce hundreds, thousands, even millions of times, and you will not lose light. Okay, so this phenomenon is called total internal reflection. And this phenomenon is the reason why fiber optic cable is so good for transmitting data. So the internet, you know, from your home to the local station is probably not fiber optic cable. It's probably electrical wire. But once it gets to that first station, and they're transmitting the signal from that station to some other station that's really, really far away, they don't use electrical copper wire. They use fiber optic cable because you can transmit the signal so much better with such little signal loss. Now, there is going to be some absorption because the glass here, as the light travels through the glass, any impurities in the glass are going to cause a little bit of the signal to be lost. So you are going to have a repeater. You're going to have a device that amplifies the signal. You know, every couple hundred miles, you're going to want to have an amplifier, or we'll call it a repeater. But if it was an electric cable, you'd need to have that amplifier like every couple of miles. So fiber optic is definitely much, much better. And it works because of this principle called total internal reflection. So in your homework tonight, they'll ask you a couple of questions about it. You just need to know the terminology. The picture that's drawn right here is not really my favorite picture. It makes it look like this thing here is not glass because it's black. So it makes it look like you've wrapped it up in some sort of rubber or something like that. But that's actually not the case. This is actually glass. And so it's actually transparent. And it's the outer layer. We call it the cladding layer. So as long as the cladding layer has a lower refractive index than the core layer, so this here is the core, okay? So as long as the refractive index of the core is greater than the refractive index of the cladding layer, then you'll get 100% total internal reflection. And it works out really, really well. Okay, so that is why people use fiber optic cables. All right, let's see what else can we talk about here. Oh, yeah, this is important. This is really good. Okay, so if you look at this photograph at the top, you'll see that we've got what appears to be water on the road. And the reason I say it appears to be water is because you can see the reflection. I mean, look right here. You can see that this car, let me make it a little thicker. So this car here, you can see the reflection of that car right here. And I mean, right here, you can see the reflection of that car. Right here, you can see the reflection of the trees. Right here, you can see the reflection of the sky. So clearly, it looks like there's water on the road reflecting everything. Well, I got interesting news for you. That's not water. That road is completely dry. What's happening is what's called the Mirage Effect. And so it's a hot day. Now, this doesn't happen on cold days. This only happens on hot days. So that the ground is very hot. It's much hotter than the air. And now the air that's really close to the ground, the air that's in contact with the ground, it picks up the heat from the ground. So the air that's really close to the ground is hotter than the air that's up higher. Hotter air has a smaller refractive index. Up until now, we've always said that the air has a refractive index that's 1.00. Well, if we were to carry out the extra sig figs, we'd find out that it's actually more like 1.0003 approximately. It depends on, well, it depends on the temperature, it depends on a lot of things. But the important thing is that it's not actually 1, it's actually 1.00 something. The hotter it is, the smaller the refractive index is. The cooler it is, the larger the refractive index is. So what's happening here is the air above the ground surface, so this is the ground surface right here. If you look at the wavefront and if you use Huygens principle, boy, Huygens principle is such a useful thing, isn't it? Aren't you glad you learned it? You'll see that the waves at the bottom there, those are longer, the wavelengths are longer than the ones up the top there. And so what's going to happen is they're going to travel further. And so this light ray is going to bend through this curved path. And so when you stand here and you look at the ground, you see light which appears to be coming from the ground. What you don't realize is it's not actually coming from the ground. It's actually coming from the truck and it's just got bent. But it looks to you like it's coming from the ground. So you see a reflection of the truck and you see a reflection of the car and you see a reflection of the trees and you think that there's water on the ground. And if you're dying of thirst, if you're in the desert and you're dying of thirst, you look over here and you say, oh my goodness, I'm saved, there's water. But then when you walk over there, you find out there really isn't water. Okay, that's called the Mirage Effect. and it has to do because of this phenomenon right here. So hopefully you guys understand that. You might see a question or two about that in your homework. All right, now we're not done yet, but we are getting close. So how does a prism work? It's time that we talk about that. And how are we doing for time? Okay, so I think we're gonna just barely make it here. All right, when you look in the book to look up what the refractive index of various materials are, you're gonna notice that the table tells you that this is the index of refraction for yellow light. Why do they say that? Well, because it turns out that the refractive index is not the same for the different colors. If you were to measure the refractive index for all the different colors, you would find out that it actually varies. And in fact, here is a graph that I went and got. This is not one for your book. This is one that I got. 400 nanometers, that's violet light. 700 nanometers, that's red light. So this right here, this is the visible part of light. Over here, this is what we call ultraviolet. And over here, this is what we call infrared. Okay. And what you see on the x-axis is the wavelength of light, and what you see on the y-axis is the refractive index. And you'll see that it's not the same. So if we look at red light, we come over here, we have a refractive index that's a little bit less than 1.46. If we look at violet light, we see that it's almost 1.48. And if we're somewhere in between, then it's somewhere in between. So the refractive index is not the same for the different colors. And so because of that, what's going to happen is that if you have, let's suppose that you have white light, which hopefully by now you guys realize is all of the different colors combined. When it hits this side of the prism, because the refractive index is different for the different colors, they are going to refract at a different angle. The blue light gets refracted more. The red light gets refracted less, so they get split out. Now, when it comes out the other side of the prism, it's going to get refracted a second time. And again, the blue light is going to get refracted more. The red light is going to get refracted less. The other colors will be something in between. And so what's going to happen is that you get a beautiful rainbow coming out the other side. The fact that the refractive index is not the same for all colors is something called dispersion. That's a word you need to know. And it would help if you could spell it correctly. It would help if I could spell it correctly. Dispersion. Okay. So what you're seeing here is dispersion. And so now hopefully you understand why you see it. Now, I don't think you're going to have to do any actual calculations in tonight's homework involving dispersion. You just need to know what it is and understand how it works. And it turns out that dispersion is the reason why you see rainbows. What's happening is you get a water droplet that's in the air. You get light coming in here. And so the light gets refracted, but because of the dispersion, they get refracted differently. And when it hits the other side, depending on the angle, you're probably going to get at least one bounce where you have total internal reflection. Depending on the angle, you might possibly get two bounces. But after that, then eventually that's going to come out. And it's going to come out with different colors going in different directions. So when you look at the rainbow, this part, you're going to see the light that was the red. Up here, you're going to see blue. Up here, you're going to see, or I'm sorry, green. You're going to see blue. It's because of a combination of dispersion and total internal reflection. That's why you see rainbows. And I think the book does a pretty good job of describing that, so I'm not going to go into any more detail. Make sure you read the book. All right, I think we've covered everything. Here's the homework. Are there any questions? Do any of you have any questions about anything that we've covered just now? All right. Well, make sure you read the book before you do the homework, because there are a couple things that I went over very superficially. I think the book does a better job of describing it. So make sure that you read it. Do problems 1 through 10, and make sure you take quiz 16B. I've noticed when I've looked at the quiz scores, you guys are starting to get lazy again. A lot of you guys are not taking the quizzes on the day that the quiz is due. Now, you know, if you take it later, I'll still give you 9 out of 10 points. Maybe I should increase the penalty there. I'm starting to think I should increase the penalty, but I'm going to stick with my rules right now. Okay. So if you think you're good to go ahead and type "bye" into the chat box, and I'll see you later. If you have a question, but you just didn't want to ask because you knew it was being recorded and you didn't like being recorded, let me go ahead and stop the recording.